Hello, and welcome to another unpracticed video of maths I find interesting. In this video, I will be attempting to show you how to take the integral of the exponential of any function, and even more interesting perhaps, how to do this integration without integrals. Let's get started. In this video, I will be going over the introduction to the problem, why it is a problem that needs to be solved, that is not as simple as it might seem at first. I will then start talking about exponential patterns and the derivatives and integrals that might lead to some solutions, then go over the actual solution using those patterns. There will be some simplification that goes after that solution to make things happy and nice, and we'll end it with an example. Before we get into the root of the video, there are some terminologies that will be really useful for understanding the actual bits of this video. Um, so if you do not understand any of these terminologies or how to use them, it'll be best if you stop now and go and try to look up these different terms so that you know what to do in each of these cases. For example, you'll have to know how to take the derivatives of exponentials, polynomials, and integrals. You'll have to know what the Taylor series is, what you won't need to understand how to solve, but perhaps just understand what a differential equation is, how to multiply different series together, because there will be multiplication of series, and in term matching. So as if you have two different power series, you have to match the matching power. So if you understand that, you will have a good time. Let's take a first approach to this. Let's say we have this exponential function. Um, Perhaps we take the Taylor expansion. The Taylor expansion of an exponential function, e to x, is given by the infinite sum as n ranges from 0 to infinity, x to the n over n factorial. And so if we just plug in f of x to being x, then that's our form for the Taylor expansion for this exponential. Exponential e to f of x equal to the infinite sum n equals 0 to infinity of f of x to the n over n factorial. We can plug this in to our integral, and that will give us this form. Using the linearity of the integral and the sum, we can switch the two, and then finally the n factorial has nothing to do with x, so it's just a constant that we can bring out. However, this is about as far as we can go. While we may be able to integrate smaller terms and all that, this f of x to the n does not have a general integral form, so it's not really nice. It can get very complicated in many examples, and so we need something more to do to handle these general cases of these general f of x. So let's go to a simpler problem. Why not take the derivative of the e to the f of x? Using the chain rule, we take the derivative of e to the power, or e to anything is just going to be e to that anything, multiplied by the differentiation of that something. So we have e to the f of x times the derivative of f of x, which we write as f prime of x times e to the f of x. We can do this similarly with the second derivative, where we just take the derivative of the derivative. And since we know that the derivative is f prime of x e to the f of x, taking the derivative of that using the product rule, take the derivative of the first, multiply the second, and then add it to the first, multiply the derivative of the second, and we get the form f double prime e to the f of x plus f prime times f prime e to the f of x. And this simplifies down to f double prime of x plus f prime of x squared times e to the f of x. Now to analyze some of the patterns that we might see in these exponentials, we had for the first derivative, we had f prime of x e to the f of x. So for the second derivative, we had this form, f double prime plus f prime squared e to the f of x. And then if we were to continue similarly, we could do the triple derivative of e to the f of x being the f triple prime plus 3f prime f double prime plus f prime cubed times e to the f of x. Now, none of these look too nice as it's going down the list, but you can notice the pattern that there is going to be an exponential function multiplied by some other polynomial function. And so let's just suppose that we have that form. Differential, let's say the nth differential of e to the f of x is going to be some function, some polynomial, call it g of n of x, times the exponential. To prove it, we need to do a little bit more math. So let's take one more derivative. If we take one more derivative, we have d to the n plus 1 over dx to the n plus 1 e of f of x, which is just the regular derivative of gnx e of f of x. We can again use the product and chain rules to figure out the derivative. And then this again just looks like another polynomial times f of x. So if we just instantiate that, if we just define this g of n plus 1 of x to being this polynomial, then that executes the recursion properly. So we shall define it as such. The nth derivative of e to the f of x being this g of n of x, e to the f of x, where g of n is defined recursively using this pattern here, gn prime plus gn times f prime is gn plus 1 of x. So for our solution, all we have to do is reverse this process. By letting n equal to minus 1 so as to go the opposite direction in derivation, the antiderivative is the integral, we plug it in and we get this g prime negative 1 plus g negative 1 f prime equal to g naught of x. But what is g 0? Well, g 0 is simply derived by taking no derivatives. With no derivatives, we just have the exponential function. So dividing the exponential function, we see that g0 of x is 1. So we have this form for the inverse, or the negative first g e times e to the f of x, which is the integral of e to the f of x, where g minus 1 is defined by g minus 1 prime plus g minus 1 f prime equals 1. So now we have this differential equation form for this multiplying factor that we can solve for. Solving for the differential equation, we define the two functions and their Taylor expansion forms. So we'll set g of x, we're ignoring the x just because it saves a little bit of space, but it's still there, it's still a function of x. And we define it as the sum of n equals 0 infinity, small g of n x dn, and f similarly fn x dn. We then have the form of those expanded forms multiplied out and plugged into our differential equation. Now, to solve the differential equation, we first have to dissolve some of the terms. We'll start with g prime, which is the derivative of g. We can bring in the derivative as is allowed by the linearity of the derivative and the sum. And we perform the derivative on this x dn by the power rule, derivative x dn being n x dn minus 1, where g of n is just a constant, so it just gets pulled out. Now we want to start with x to the 0, so we have to shift n to n plus 1, as n at 0 will just give us 0 x to 0 divided by x, which doesn't make any sense. So we just shift it over. Now we have the product of these two series as our second complication, and it's going to be g times the derivative of f. Recognizing that these two series are completely independent of each other, we can give them their own indices, I and j, I for g and j for f. And then we're going to bring one series inside the other completely, as it is just a constant. J is completely independent of I. Now, the f has been already taken into its derivative form as shown with the g prime. Then we can do similarly, bring the g of I xi inside the j sum, as once again, it is completely independent. It is just a constant. It doesn't matter. So that allows us to write the sum or the product of the sum in terms of the nested sum in this form. Now we once again rewrite j to be j at 1 as j at 0 is this irrelevant. Multiplying by 0, adding 0 is not going to do anything. So now we let n equal to I plus j minus 1, which is that power in the exponential of x, and which will also require the I to be equal to n minus j plus 1, which allows us to rewrite this again as g times f prime is equal to the sum as n equals 0 to infinity of overall this as j ranges from 1 to n plus 1, where the n plus 1 is a new limit on j so that I is not less than 0, of j times g of n minus j plus 1 f of j times x to the n. Once again, we remove the x to the n as it is completely independent of the j, and now we have a form of sum of n over the xn multiplied some constant. We can then plug it into our differential equations to get this form. We can also rewrite 1 as its own sum, as n goes from 0 to infinity of the Kronecker delta of n at 0 times x dn, where the Kronecker delta of n at I is described as being 1 when n equals I and 0 otherwise. And so rewriting it, we get all these different terms, which may look a little not nice. However, when you recognize that for each value of x at each power of x, the value must match, then we get to ignore all these series and all these x to the n by saying each value of x to the n must, or the coefficients rather, in front of each value of x to the n must match on either side of the equal sign. So we just get rid of that. We rewrite in just these constant forms. Now g of n plus 1 is all alone, so we can separate it, and thus we retrieve this recursive form for the g of n plus 1. Maybe some of you might not like to have a recursive form for these constant coefficients, but at least it is something. Reminder that the alternative is to do infinitely many infinite products of infinite sums, which is not so nice. However, there is still one issue to address, and that comes with g naught. If we start to actually unfold these g's, we get g1, which is what we do when n equals 0. The Kronecker delta of 0 at 0 is 1, so we have that 1 there, minus f1 g naught over 1. We do the same for g2 with n equal to 1. The Kronecker delta of 1 at 0 is 0, so it does not apply. And then we multiply out, getting the minus f1 plus f1 squared minus 2f2 times g naught over 2. We can do similarly for g3. Once again, the Kronecker delta is not there, and we get f1 squared minus 4f2 plus negative f1 cubed plus 6f1 f2 minus 6f3 g naught all over 6. However, our problem is that g is never defined in this system. So what are we supposed to do about it? Well, we can't do anything about it directly right now. However, what we can do is, once again, use pattern recognition to see that each of our g's has a g naught and a not g naught value. So we have a constant plus another constant times g naught. So let's just write our gn's in this pattern. So we're going to rewrite our gn as being gn star, where it's going to be some constant disregarding g naught, and added to gn0 times g naught, where it's going to be all those values that are attached to the g naught. We can plug this into our g series Using the linearity of the sum, we can separate them out. And then once again, we have G naught as being constant in terms of n, so it is brought out. And that allows us to write two separate series terms, or two separate functions, where we will define G star of x as being the sum over Gn star x to the n, and C of x, multiplying this G naught, being defined by Gn 0 times x to the n. It is important to note that this G star is of order 1 in this case, where it'll start with x to the power of 1 rather than x to the power of 0. This will be important for later. As a quick aside, we really do need to evaluate e to the f of x at least a little bit in order to continue with our understanding of what G naught is. But we will only be doing a little bit. As we've already exclaimed, this summation form, this expanded form for e to the f of x is still a little bit too hard to work with. However, if we work with just zero order, then we can get somewhere. So if we consider the power of f of x dn, we have the sum to the power of n. Which again doesn't look so very nice. However, what we can do is, taking the sum, we can separate out the zero order term, f naught, and all the terms after that from I to infinity, and we take that to the power, which still doesn't do much. However, what it does allow us to do is just rewrite it in a simpler form to say if f naught plus this order of x polynomial to the power of n, where this O just denotes that it's an order, and this is an x to the 1 for first power of x polynomial that is inside this sum. To analyze this, we just use the binomial expansion, which is defined as a plus b to the n, being the sum as I equals 0 to n of n choose I, a to the n minus I times b to the I. So if we recognize that f naught is our a in this case, and our order x polynomial is our b, we have sum I 0 to n, n choose I, f naught to n minus I times o to the I. We can then take out each of these terms. So we have the zero order term n choose 0, f0 to the n plus n choose 1, f0 to the n minus 1 times order of x, and then so on and so forth. However, we recognize that only the first term has no order x, so it alone is its own constant value. It alone has all of the order x to the 0 terms, and then we're going to have another continuing polynomial of at least order x. So we'll say it's going to be order x, and we'll denote it with an n because it is still going to be dependent on these n. But now we have a reduced form for our exponential of f to the n. So replacing our f to the n with this zero order f naught to the n plus our order 1x, and we can again separate out the two sums as it is a linear operator, and we recognize the first sum as being our exponential again. This is just going to be the exponential of f naught. So we can just write it as exponential of f naught plus, again, another order of x polynomial, which we are not going to concern ourselves with the details of, only that it is of order x. Now we can compare the integration, so we can think about how our form is actually going to work. We plug in our two different forms, for g being g star plus g naught c, and our e being e to the f naught plus this order x polynomial. Actually performing these operations, we have the multiplication of the g and e to the f, giving us g star e to the f naught plus g naught e to the f naught c plus g star plus g naught c all times the order x polynomial. and that's going to be equal to the integral on the other side, where the integral of e to the f naught is just an is just an integral of a constant, so it's just going to be that constant times x, e to the f naught times x. The order x polynomial is going to be raised by 1 power, as it is the opposite of differentiation. So it is going to come to an order x squared polynomial, and then that is going to be added to a constant of integration, as is proper to do in these formats. Now we are only concerning ourselves with order x0, x to the 0, all the constant terms. So anything of order x or greater, we can just ignore. For g star was defined as being order x, so we ignore that. The order x polynomial multiplied by another order polynomial is going to be at least order x, so we can get rid of that as well. E to the f naught times x, that's obviously order x, that's an x right there, and then order x squared is greater than order x, so that is also ignored. Then we also only have the the constant term for c of x, and that allows us to write this form. And what we see here is that g naught is very well related to c by just another couple of constants. And so since the constant of integration can be any constant, what we get to conclude is that g naught is our constant of integration. So it really doesn't matter what it is, as it is going to just come out as being a constant in the end of things. So why don't we just let it be 0? Letting g naught to be 0 and plugging into the g1 form, we find that g1 is equal to 1 minus g0 times f1, which is 0, so we get that g1 is just 1. And so we have that g1 is also generally determined. Wonderful. So now we have our solution set, where we have the integral of the exponential of any function of x dx is given by another function, g of x, multiplied by the exponential, where the g of x is given by the infinite series of these g of n times x dn, where the g of n are defined recursively by g of n plus 1 equal to minus the sum as j equal 1 to n plus 1, j gn minus j plus 1 fj divided by n plus 1, where the seed is that g of 1 is 1. And so again, it's not the nicest form, it's not the most closed form possible for a given f, but for any general f, this is just about as far as we can get without having to deal with infinitely many infinite series being multiplied together. So this is still good. As an example, why don't we go with the simplest example, e to the x. For e to the x is its own function, and that can be written in the sum as the Kronecker delta of n at 1 times x to the n. So again, it is going to retrieve that n equal to 1 term, so it'll just be n x to the 1, which is our x. And so our g of 1 will be 1 for that value. G of 2 equal to minus g1 f1 over 2, and our f1, since it is the first, or the x to the 1 term, it is 1 for our function of x, so f1 is 1, and that gives us minus 1/2. Our g3 minus g2 f1 plus 2g1 f2 over 3, which then we get out all our terms. G2 is minus 1/2, and we multiply by f1 is 1, and then we add 2 times g1, which is 2, multiplied by f2, which is 0, divided by 3, that gives us 1/6. You can do similarly for g4, which returns minus 1/24. And then we continue on with g5 being 1 over 120, and it continues on and on. Hopefully at this time we can understand that there is a pattern occurring. If we actually write out our g of x, we get g of x equal to x minus x squared over 2 plus x cubed over 6 minus x to the fourth over 24 plus x to the 5 over 120 minus dot 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 dot, on and on and on. And this is very simply recognized as being the expanded form of 1 minus e to the minus x. We just multiply that by x and we get our solution to the integral of e to the x being 1 minus e to the minus x times e to the x is e to the x minus 1, which again is recognizable as being our solution to the integral up to that constant term that we just ignored. Now, if you don't like the fact that we have this minus 1 term, there's also another way that we can do it. Alternatively, if we let g naught be to the inverse of some constant, where that constant is a slope in a linear line for f of x equal to ax, we can instead try to go through this solution with g naught not equal to 0. We find that g1 would be 0, g2 would also be 0, and it's left up to the reader, but it should be a simple case to solve to show that g of n for n not equal to 0 is also 0. And so that leaves us with what we would expect for the integral of e to the ax dx being 1 over a, our g, times e to the ax. And so it works. Although we showed that the g naught equal to 0 case is not always the simplest case to work with, we can see that it works whatever g naught we choose, and there is always an appropriate one that can make situations easier. Life is easy with it. So we will leave it there. As an exercise, I'll leave you with this question, as if you can solve for the c of x that was multiplied by that g naught. I'd like to see if you would try your hand at that. I think it was a fun exercise that I went through, and so I want to share that with you. Anyways, have fun with this knowledge. I'm still not practiced with these kinds of things.